page 6 of the IO notes. So we're talking about polling, and there's two things about polling. One, it's simple. You saw that polling loop, it was one line. But there's a consequence. It's inefficient. If you've got other work that your processor could do, I suppose you could go do some work and come back and check if that data is ready, and then do some more work. We're going to see that interrupts are a better way to handle it in that scenario. Just to give you an idea of how efficient it can be, I mean, this is an extreme example, but let's just look at our polling loop in ARM assembly language. So in lab 1 of the course, you're going to be using the debugger. And in the debugger, you can step through your program and you can see the assembly language for the code that's been compiled. And so the code for our loop looks like this. I may have changed a register name or two, but this is essentially it. You do not need to understand this. I'm really just illustrating a point. So LDR is load into register, and B is a modifier on that. It means byte. So load a byte into register 1, and where it's loading from is pointed to by the contents of register 0. So register 0 is a pointer to the LSR. This is a pointer to the line status register. And let's do our comments in green. So comments in this ARM assembly are prefaced with a semicolon, and what we're doing here is we're going to load a byte into R1, and it's coming from the line status register. Okay, next statement in our loop. Test R1, and what test does is it does a bitwise AND. This is an immediate operand, which means it's a constant that's embedded in the instruction. There's our 0, 1. So what we're going to do here is test bit 0. So it's going to do a logical AND or bitwise AND of the value in R1 from the LSR and that constant. And the third and last line of the loop is branch if equal. So if the result of that logical AND or bitwise AND on the previous line, if the result is 0, we're going to go back up to loop, and if it's not, then we exit the polling loop. So if 0, repeat. And loop is not a keyword in ARM assembly, it's just a label, a way to identify which line to go back to. And in ARM, it's a pipelined processor. The Cortex-M3 is a 3-stage pipeline, so it's a pretty simple pipeline. It can execute most instructions in one cycle. So actually, it executes most instructions in 3 cycles, but it overlaps the execution of 3 instructions. So on average, you finish 1 instruction every cycle. So first statement, second statement. The exception to that are loop instructions. They add a little bit of overhead to the processing, and so on average branch instructions take 2 cycles for a total of 4 cycles. The Cortex M3 clock rate is 96 megahertz, 90 million cycles per second. What we can get out of that, the polling rate how many times we can execute this loop in one cycle is going to be equal to 96 times 10 to the 6 cycles per second, divide by the number of cycles to execute one iteration of the loop. We've counted that up there as 4 cycles per loop, and so that gives you 24 times 10 to the 6 loops per second, or poles per second. So pretty fast, but how fast is that? So let's make some assumptions. First assumption is that the UART is receiving keyboard data. So keyboards are fairly slow input devices because it depends on a human to type. And let's assume that a fast typist can do in the neighborhood of 70 words per minute. I looked that up somewhere, and let's assume that a word is on average 5.1 characters. So in English, it will depend on your language, is 5.1 characters per word. Depends on which idiom you're using, I guess. So if it's Shakespeare, I'm going to guess that the average will be higher than that. If it's text chats, it'll be a lot shorter, and so on. But it's a reasonable assumption. So what we want to figure out is how many of these polling loops are we doing for every character that we receive. So I'm going to call the rate at which we receive the data rate, probably a good thing to call it. So how many characters are we receiving per second? And so that's going to be 70 words per minute over 60 seconds per minute. So that gives us words per second. So that'll just be a little over 1 times 5.1 characters per word. So now we've converted it into characters per second. And then we really want bytes per second, so we can just multiply that by 1 byte per character, and that gives you 5.95 bytes per second. So that's how fast we're getting the characters from the keyboard. So the average polling loops per key press, and that is going to be equal to the polling rate. And what do we do with the data rate? We got loops per second, we got bytes per second. Pretty simple, we just divide the polling rate by the data rate. So that's 24 times 10 to the 6 loops per second over 5.95 bytes per second, and that's going to give us 4.03 times 10 to the 6 loop iterations per byte, or polling loops per key press. So about 4 million, which seems kind of excessive. Now, one thing that I've left out of the equation is the time that you actually spend processing the data. So you'll get a key that's been pressed, you read in the value, and then you might add it into a buffer in memory. A buffer is just an array of bytes in memory. Or you might do further processing. So this it ignores time spent processing the data, but it does illustrate the point that you can loop a lot of times between each byte that you receive.